Hello again, everybody, and welcome back. We're continuing our Chapter 2 notes on kinematics, and this is Section 2, you might call it Section 2, as corresponds to our honors physics textbook. And we're going to be talking about speed now, and also another quantity that's very much like speed, but has one major difference. So speed you're familiar with because if you're a driver, you know that in front of you at all times is a speedometer. And it tells you how much, it basically tells you your rate of motion, as it says right here. That it means how much ground you're covering in a certain amount of time. It doesn't matter if you're going north, south, east, or west. Your speed is always positive. So as such, speed is what we call a scalar quantity. Scalar, which means it only has a magnitude, it only has an amount. It doesn't have any direction. Or at least if it does have a direction, the direction doesn't matter. You could be speeding north, south, east, or west, and the cop will still pull you over regardless of what direction you're going in. All right, so really it's just the magnitude of how much ground or how much distance you cover in a certain amount of time. Okay, so average speed, and we're going to indicate this as V average. So that little subscript there, AV, stands for average. And you might ask why V right now? Well, we're just going to call it VAV for the time being, but that just simply means your total distance over your total time. In fact, I'm going to put that in parentheses here. Total distance over total elapsed time of a given trip. Okay, so however long it takes to go some distance is your average speed. So even if you go faster or slower in between, it doesn't matter. It all evens out to if you were to go to a constant speed for that whole amount of your trip right there. And if you paid attention on my previous section of notes when I was discussing displacement and distance, I accidentally said that the units for distance are meters per second. That's not correct. It's just meters. But for speed, it is meters per second. Meters is a certain amount of length, right? And per second is a certain amount of time. And those are the dimensions that indicate speed, covering some sort of speed. Okay? Incidentally, both distance and both elapsed time are scalars. Because as we said before, distance, we don't care about the direction. All right? Let's do a quick little example of calculating speed with this next little problem we have right here. Okay, so you have three different speeds actually. You're driving your car, and like I said a minute ago, you almost never, I would venture to bet, you never drive exactly the same average speed for a whole trip. You drive at various different speeds. This guy drives 5 miles at this speed. What's MPH? You know what that is. It's miles per hour, right? Oh, I made a little mark at the bottom here. Miles per hour. And then he drives another 5 miles at 40 miles per hour and 5 miles at 50 miles per hour. So the question is, what is the average speed? Or you might say the total average speed for that trip right there. Okay, well, recall back to a slide ago. We said V average speed is the total distance or the total time. All right. So we could actually start writing that out. All right, let's just calculate the average speed. What is the total distance? Well, we have three different distances, right? We have 5 miles and 5 miles and 5 miles, and so let's just add them up. All right, the numerator is 5 just 5 miles. Messed that up. 5 miles plus 5 miles plus 5 miles. Okay, great. The problem is we don't know the amounts of time that is spent at these different speeds right here. We need to know time 1, and I'll write this in black because that's what we're solving for right here. Time 1 plus time 2 plus time 3. We have three different distances, 5, 5, and 5. That's easy, but these three different times we do not know. However, we do know that, as we said a minute ago, V average, that is the average speed, is distance over time, all right? So couldn't we find the time by saying this, that time is going to be distance over your average speed. We're just rearranging them to solve for time right there. So what we should be able to do is solve for time 1, time 2, and time 3 simply by taking the distance, the 5 miles, and then dividing by the various different miles per hour that were driven. All right, so I'm going to erase these right here because we're going to need that space in a minute. Okay, so look, we're going to go down below right here. And in blue, I'm going to calculate, so time 1. Time 1 is going to be the distance 1, which is 5 miles, divided by the speed at which it was driven. So the average speed for that little segment right there, 30 miles per hour. Miles are going to cancel out, and then we're going to have just a unit left in hours, which is good because we want a unit of time. So 5 divided by 30, I get 0.167 hours. I don't know exactly how many minutes that is offhand, but that's okay. Time 2. What time is that? Well, that's 5 miles. The distance driven divided by 40 miles per hour. All right, and that's going to be 0.125 hours. And our time 3 is going to be 5 miles divided by 50 miles per hour. All right, and that's going to be 0.100 hours right there. All right, I probably put too many significant digits there, but that's okay for now. All right, so we have our 3 times. We got our 3 times by taking our distance and dividing by the velocity that was driven during that distance. And so it told us how much time was spent driving that velocity that distance. So now what we can do is we should be able to just stick them right in the denominator right here. And I'm doing my best to erase that T1, T2, and T3, but it's not working for me. So we're just going to rewrite it again. Okay. So actually, we can simplify that. The numerator, that'd be 15 miles, right? 15 miles divided by our 3 different times. And our 3 different times are 0.167 plus 0.125 plus 0.100 hours. There's our h right there. And that should give us our total average velocity for that total trip. So even though he drove various different speeds, this speed, 5 miles at this speed, and then 5 at this speed, and 5 at this speed, we've been able to calculate the entire average velocity as if he were driving one speed the whole time. All right? So 15 divided by the sum of those 3 values right there, I get, what do I get? Okay, I get 38. The average velocity is 38 miles per hour. Now, I rounded that to 2 digits right there. So V average equals 38 miles per hour. And that is the average velocity of that whole trip. So ignoring all the different, or if we were to take all those different velocities and different distances and average them out, that's what we would have. So somewhere between 30 and 40 sounds about right. All right, so that's an average speed example that that we use by solving for the times here, by taking distance over velocity, getting our times and putting our total distance over our total time, and we have our total average velocity. Oops, and I just made a mistake. What did I just say? I said average velocity. Well, that's the one term that I'm about to talk about in just a second. We've been calling it V average, even though it's really average speed, but we've been referring to it as VAV because really, when we talk about speed in physics, we're really more focused on not speed, but velocity. And velocity is the next kind of topic we're going to talk about right now. So average velocity is the rate of change in an object's position. Right? Well, that sounds an awful lot like speed, right? But this is different in that velocity is not a scalar quantity, but it's a vector. A vector quantity. And very much like displacement. Remember, we compared position or distance versus displacement. Displacement could actually have a negative value. Now, you can't go out and run negative 10 miles, But if you consider the direction that you're running to be the negative direction, then I guess you can run 10 miles in the negative direction. We just put the negative out front. Same thing with velocity right here. This displacement right here is a vector, which means it can be positive or negative, which means you could be running, I don't know, how fast would you run? 5 miles per hour? That seems kind of slow, maybe. You would take that and you could run 5 miles per hour in the positive direction, or you could run negative 5 miles per hour in the opposite direction. We can call it that because velocity is a vector quantity. Now, as I said before, we're going to measure it in meters per second. That's our standard international system units. But it's very important that the sign tells the direction right here. So if we consider this to be the positive direction, and this to be the negative direction right here, if you are going some distance, so negative delta x, negative displacement in a certain amount of time, we would call that a negative velocity. Okay, now I keep writing those arrows over the v and over the delta x right there because those are vector quantities, and vectors are what enable us to have a positive or negative sign in front of it. Okay? So, let's do this example right here with average velocity. This is going to be different than average speed. All right, it's slightly different because we are taking into account direction, which could be positive or negative. Okay? So we have a sprinter sprinting 50 meters in 8 seconds. Okay? So let's start writing down what we know, writing down our givens right here. Okay? Our displacement equals 50 meters. Okay, we're going to assume maybe that the starting line, we can call the starting line the origin if you want, although you don't have to, but we're told that he covers 50 meters, so that's the displacement. That is the vector quantity of him covering some amount of ground. And the time that is elapsed equals 8.00 seconds. Okay? He stops and then walks slowly back to the starting line in 40 seconds. All right, so we'll call time 1 that. Time 2, we're going to call 40 seconds. He must be pretty winded right here because he's walking back, taking a longer amount of time. Question is, you know what, we'll call this displacement 1. Question is, what is the displacement 2 right here? How much ground does he cover? Well, distance-wise, he walks 50 meters back to the starting line. But if we're talking about this in terms of a vector quantity, that is a displacement, he's really displacing himself negative 50.0 meters back to the starting line. Negative 50.0 meters. Okay, does that make sense? So here's our person right here. We'll call this the origin. All right. That's the starting line that he's at. The finish line is right here. And we're going to call this direction positive. He runs real fast down to the end, 50 meters in 8 seconds, and then he walks back slowly back to the starting line. But you'll notice that the walking back is in the non-positive, or that is the negative direction. So that's why the displacement is going to be negative right here. Okay? So if we call the sprint direction positive, so he's running this way real fast, we call that positive. What is A, the average sprint velocity, okay? B, the average walking velocity, and C, the average velocity for the whole round trip, okay? So let's take this, and in fact, let's do this in different colors. I'll do A in red, B in blue, and C in green, okay? And that should say for, not fro, but that's all right. A, right here, the average sprint velocity. All right, well, average sprint velocity is the displacement. I'm going to put a vector sign over the average velocity right there. The displacement 1, because displacement 1 is where he's sprinting, over the change in time, right, over time 1. So that's going to be 50.0 meters in how many seconds? That's 8.0 seconds. 8.00 seconds. So what's 50 divided by 8? I'm going to guess that's 6 something. 50 divided by 8. I'm getting this wrong. 50 divided by 8 is, divided by 8, there we go, 6.25. I guess I should have been able to do that in my head, maybe. All right, 6.25 what? Meters per second, because that is the units that we have right here in our displacement over time fraction right there. All right, 6.25 meters per second. Not too shabby. B. What is the average? So we'll call that average velocity 1. Oh, and I said B, we're going to write in blue, right? Let's change to blue so we can separate them out. B, what is average velocity 2? Well, it's the same thing. It's our displacement 2 over our time 2 right here. So what is our displacement 2? Well, it's negative 50. Got that wrong, not 5.0, 50.0. 0.0 meters in 8.00 seconds. And so that's going to tell me that if we do the same numbers but with a sign, it's going to be the average. Oh, I'm sorry, no, not 8 seconds. It takes a longer time to get back, right? 40.0 seconds. All right, so 50 divided by 40, I should have been able to do that in my head too. 1.25 meters per second, right? Not right, right? What did I miss? I missed the fact that there is a negative sign. And so he's walking slower and he's walking in the negative direction, which means he has a negative velocity. So the speed is less, but the velocity is actually negative because he's walking in the negative direction right there. Okay? So, part C, what is the average velocity for the total trip? That's TOT right there. What is it? All right. Well, what is the total displacement? You might say, I want to put x1 for the whole trip. x1 is here, or x initial, and x final is here as well. So he goes down and then comes back. So really, how far is he displaced? He's displaced 0 meters for that whole trip because given the whole trip, he winds up back at the exact same point that he was when he started. In how many seconds? Well, 8 seconds plus 40 seconds, that's 48.0 seconds. Well, 0 divided by anything is going to be 0. So on average, for the whole trip, he has a velocity of 0 meters per second because he makes just as much, he makes just as good of time as somebody standing there at the starting line the whole time because he winds up back at exactly the same place. Okay? So that's our first example on average velocity. I'm going to stop right there for this video. I'm going to pick up with graphing motion and kind of plotting coordinate systems and looking at other kind of XY graphs, but that'll be in the next section. We are still in, that'll be in the next segment of this section. We're still in section 2 of chapter 2. This will be, we'll call the next section 22B because this one's getting pretty long. So I'll see you in the next one. We'll pick up there.